Hello everybody and welcome to this lecture titled Physical Security of Internet of Things Communication. My name is Professor IoanTudosa. I come from University of Sannio, Benevento, Italy. So, we saw last time the first two parts, part 1 and part 2, regarding the hardware security aspects and measurements aspects regarding the security of Internet of Things devices. And this part 3, we will speak about a method developed for cable diagnostic by using a passive measurement method. What I want to say you in few seconds is that this method was published in a scientific paper on IEEE Instrumentation and Measurement Transaction journal, which is a famous journal and top lead journal in this field. If you want to dive into this paper, you are welcome, and if you have any question, just do not hesitate to write us emails to one of us authors. Regarding the experimental setup that is described in this paper and that is proposed, here you can see that a transmitter receive the digital data, the bitstream data, okay, that sends through a dual wire cable data to a receiver. This dual wire cable is cheapest, that it is commonly used in Ethernet cable for high-speed data communication. The main idea of this measurement method is to detect anomalies that it may occur in a point of the cable by using a so-designed low-cost instrument, which is composed by a low-pass filter, an analog-to-digital converter, and a microprocessor. Our idea is to use machine learning algorithm to do an automatic classification of the anomaly type that it may be present or it may occur during the function of the transmitter and the receiving of the information between two peers. For example, here on the figure down, you see a Raspberry Pi as an example of a transmitter sending some data to a router. Okay. This connection is a normal Ethernet cable, and we just collect this signal, the signal carrying out our communication information, by using a simple differential amplifier connected to a low-cost data acquisition system that emulates actually this part of the figure here, which is a red PTI model. Okay, and the machine learning algorithm you may apply offline on a personal computer and so on. Okay. So based on this experimental setup, on the scientific paper that we have published, we designed a laboratory advanced setup consisting of an arbitrary waveform generator 420 from Texas, from Tektronix, and the same Tektronix technology and a very wideband oscilloscope working at the data acquisition of 6.25 gigahertz. So at this speed, it almost 12.5 gigabytes of data per second that the oscilloscope acquires to monitor the data that is the signal generator it sends through the cable to be acquired by the oscilloscope. The test signal, in this case, it was used a pseudo-random binary sequence. This is a deterministic binary sequence that mimics the random data, and it is commonly used for communication channel testing. And it is used a pulse amplitude modulation technique, working at a symbol rate of 125 megahertz, having an amplitude of 0.5 volt, and the length, the payload length of 104 symbols. Okay, to mimic this setup. Regarding the anomalies that we developed three anomalies. the first one is air exposed conductor, as you can see here. The second one is water exposed conductor. So the exposed conductor is immersed in water. And the third one is taping. Okay, just as another cable is connected to listen the data from our communication channel under test. For each anomaly, 10,000 sequences of Y of n signal acquired were acquired by the oscilloscope, providing a total number of 50,000 records, where 40,000 are with the anomalies, and the other remaining 10,000 are without any anomaly. Okay, for the consistency of the experiment. So regarding the implemented machine learning method, the algorithm takes as inputs the decoded sequence, okay, the decoded bit stream, okay, and the acquired signal. This is acquired by the oscilloscope, and this is the decoded by the receiver circuitry. Once we have this available, the decoded sequences are used to obtain the impulse response of the cable that is estimated, and this is noted by P of n. Okay. The time domain and frequency domain features are extracted from the signals y of n and P of n. Okay, in this case, having y of n and P of n, we do feature extraction to obtain time domain and frequency domain features. And once we have, for each case, those features being extracted, we train a decision tree classifier which provides as output the type of the anomaly. Okay, so quite straightforward, the technique. Regarding the feature extraction, following features have been considered for both y of n acquired signal and p of n the estimated impulse response. The time domain are used like standard deviations, skewness, shape factor, root mean square value, peak value, average, kurtosis, impulse factor, crest factor, clearance factor. Regarding those frequency domain, the top 10 discrete Fourier transform coefficients, frequency bins corresponding to top 10 coefficients, and the band power of the signal in the frequency domain. To assess the sensitivity of these features to the anomalies, one-way analysis of variance, ANOVA test, has been performed. This ANOVA test is a statistical method that is used to evaluate whether feature means differ significantly across the anomaly classes. So once we launch an ANOVA test, we will obtain a sort of representation between each feature ID respect to other feature ID and in a sort of matrix, one by one, and we see these main differences between anomaly classes. After this analysis, just 25 features were adopted that corresponds to F values greater than 2000. For example, P value lower than 10 as minus 4, and with correlation lower than 0.8. Okay, so we stop at this number. Okay. Once we have selected the features, we have started to perform training and validation trials. And for the training, 8,000 records have been considered for each anomaly class, from where 80% of the data set, in our case, is represented by these 8,000 records, while for the testing, the remaining 20% were used. So the binary palm sequences in the training are not correlated to the ones in the test. This is important to remember. And we choose a 5-fold cross-validation method that has been adopted in the training phase. Okay. So here we just do a short presentation of the main results. We have a confusion matrix showing an average accuracy of 93.9%, an average precision of 95.5%, an average sensitivity, the so-called recall, that is 92.4%, an average F1 score of 94.0%. Regarding the previous results from the training phase, the lowest true positive rate is obtained in the case of conductor exposed to air, where the classifier confuses this anomaly with a normal case one, as you may see here. Okay, so here 0 means anomaly length, so there is no anomaly, the true case. Okay, and starting with the length of anomaly at maximum half meter, we can watch the confusion between having anomaly and not having anomaly with a normal cable. Regarding a demonstration that I consider you may test by yourself privately, you can access our data set by typing on a browser this address. You will be directed to IEEE data port. You have to log in by yourself, and here you have the datasets file, which are almost 14 gigabytes. You have to download them, and once you downloaded them, you may start MATLAB, and to load these tabular files, point mat files, and once you load each file, you will see here their representation on your workspace as tables. So these tables, for example, are composed by different information like the signal, byte sequence, type of defect, length of defect, and so on. So these four tables are table with air exposed conductor, table with normal nominal parameter of the cable, table with the tap, the cable being having a tap anomaly, and the table with water exposed conductors. Okay. Once you have loaded these tables on your workspace in MATLAB, you can run, we may give you two scripts to run a feature extraction script, for example, from these tables. And this is a simple line-by-line calling a specific MATLAB function. So it is nothing special in this script running. And these allow you to obtain the final features that are needed, are required for training phase and testing phase of our machine learning algorithms. So once we obtain this final feature in a tabular form, you'll see a new point mat file that has been generated by the MATLAB. Is the same in a tabular form. For example, on each column are different features, and you see their names like clearance factor signal, crest factor signal, impulse factor signal, kurtosis signal, mean signal, and so on. So different names and different values that have been calculated previously by running that script. Now, if we have obtained this final feature table, we may start to run from the tab apps in MATLAB to choose a machine learning or a deep learning. In our case, we choose classification learning. So you have to find by just typing class here, and it appears this specific function. And once we launch this, a new window will appear. We have to start a new session and to load data from workspace. So once we have this, a new pop-up window will appear. we see here that you will see here that the data set variable is named. So in our case, the table is named features final, okay, and shows us how many columns and how many data per column is present. From data set variable here, we choose 4 unique IDs for the 4 considered anomaly as a type of defect. You see them here. You can just scroll down and see them. We implemented a 5-fold cross-validation technique. So here you can just change these parameters or more or fewer cross-folds you may test. And once we have set all of this, we may start the training session by clicking the Start Session here. Once the learning phase has been performed, you may obtain a figure like this, which represents a scatter plot between the classes that we specified during the configuration of the learning phase, or with air, normal, tap, and water. So you can put on Y or on X different features and to see if there is some important relationship between each of them. Once you have obtained this, the next step is to do the analysis of variance. And for this, in MATLAB, it's quite easy to do such analysis of variance, ANOVA test, by clicking feature selection here. And it appeared this default feature selection tab, where you just have to click on the ANOVA button, and after it runs, here you have the obtained results. Once we have obtained the results from the ANOVA test, we have to select the decision tree as a part for the validation of the anomaly learning phase detection. So once you click here the find tree, okay, you just click the button train. Here, after that, before to launch the button on the train all, of course we can model the hyperparameters of the learning condition. Here we have some misclassification cost that you may let by default and so on, or you may change parameters and validation. Once the learning phase has been validated, we obtained the confusion matrix with number showing by number of observation or by running clicking on this button to see the percentage, okay, in terms of percentage, the true class versus the predicted class. This means the confusion matrix. And once we have finished with the learning phase, we just have to switch on the test data. By clicking here on the test data, we have to import from workspace the same our test data, and just select the same feature final table that previously was loaded. Okay. Once everything is okay, we just have to click the button OK. We just run the test button to test all for all the anomalies. And once the test is performed, just click on the confusion matrix. A tab appear here, and the same you can observe the percentage of your results and so on. So once everything is computed, here is just a summary of our test. And once everything is done, just you may export your model to workspace to save it and so on. And quite easy part. Thank you for watching this video. If you have any question, just write me an email and I will be happy to answer to your questions.